Hi everyone, welcome to goclasses. In this lecture, we will solve gate PYQs of cache memory. With complete analysis, we are going to solve all the gate PYQs. Okay, so take your copy pen. I will solve it, and you also solve together. Let's solve all the questions together. So take your copy pen. Let's solve GATE 2008 question. In GATE 2008, this question number 80 and question number 81. Basically, this is paragraph type question. This paragraph is given, and based on this paragraph, there are two questions. You can see the same paragraph is given in these two questions, question number 81 and question number 80. Okay, and basically, based on this paragraph, two different questions have been asked. So let's solve it. Let's read this question. Let's read the paragraph here. Consider a computer with a four-way set associative cache of the following characteristics: 1 MB main memory, word size 1 byte, means one word equal to 1 byte, block size 128 words, and cache size that is 8 KB. And the question is basically asking the number of bits in the tag field, set field, and word field. Okay, and you can see in this question number 81, which has the same paragraph, but the question is asking that for this memory location, for this memory address, we need to find what is the tag field. Okay, so this is a simple question. First of all, let me tell you, what about this cache size, cache memory size? Do we consider the tag directory size when we find the cache memory size? When we talk about cache memory size, then do we consider the tag directory size also? No, we do not consider. So we have already seen this, that cache memory consists of data array and tag array. So in the cache memory, there is a data array, there is a tag array. This tag array is also called tag directory. But remember, when we say, when we discuss cache memory size, the capacity of cache memory or size of cache memory, then remember, we only discuss the size of data array. We do not include the size of tag array. But in the question, if they say that include the tag directory size also, then we will include. Otherwise, we will never include. Okay. And remember, in this data array, we have the blocks that we fetch from the main memory. From the main memory, we take the block of data and we put it in the cache memory. So let me tell you, this block of data from the main memory, this block of data we put in the data array. So in this data array, you can see, for example, this is one line. Okay, this is a one line. Okay, and remember, with every line in the tag array, in the tag directory, corresponding to every line, there is a tag stored. Okay, so here we store the tag. Very simple. So corresponding to every line, we store tag in the tag directory. So this is also a physical storage, this is also a physical storage. But remember, when we consider the size of cache memory, then we are only considering the size of data array. So what will be the size of cache memory? That will be size of data array. And what is the size of data array? That is the number of cache lines. How many lines are there multiplied by the line size? Yes or no? Very simple. So let me tell you here, in the cache memory, we have cache data array, also cache tag array. Tag array means tag directory. In the tag directory, we store the tag. We also store, valid bit, dirty bit, basically some status bit, some extra status bit also we store in the tag directory. So basically, in the tag directory, we store the metadata, but the actual data that we bring, that we fetch from the main memory, that actual data, that actual blocks, we store in the data array, cache data array. Very simple. Okay, so you can easily see the capacity of cache memory, the size of cache memory does not include the tag directory size. The size of cache memory does not include the tag bits, valid bit, dirty bit, and so on. Okay, so very simple. So what will be the size of cache memory? That is the size of data array. And what is the size of data array? That is basically number of lines multiplied by line size. Very simple. So in this GATE 2008 question, you can see in these two questions, question 80 and 81, we are using the set associative cache memory. So let me tell you, in the set associative cache memory, we can divide the physical address, the main memory address, we can divide into three fields. So you can see this is the main memory address, and this main memory address we can divide into three fields. There is tag field, index, and offset. Okay, so you can see, and remember one more thing, whenever you find how many bits for offset, how many bits for tag, so always go from right to left. Means first you find how many bits are required for offset, then you find how many bits are required for index, and then you find the number of bits required for tag. So remember, whenever you divide the main memory address into three parts and you are finding how many bits are required for each field, then always go from right to left. Okay, here let me tell you, this offset, this is basically your byte offset, or you can say this is basically your block offset. What is block offset? Block offset means within a block, if I want to refer to a byte, then how many bits I need. Okay, so I can say within a block, the address of a byte. Okay, how many bits I need to address a byte. So that is called block offset. This block offset, this is also called byte select. Why this is called byte select? Because within a block, if I want to address a byte, then how many bits we need. So basically, using this block offset, what we can do within a block, we can select a byte. Okay. So remember, this block offset, this is also called byte select, or this is also called byte offset. Very simple. And we can find this, the number of bits required for block offset, we can find from block size. Okay. And what about this index? In the set associative cache, this index represents the set number, or I can say this is basically the set index or set address, or I can say set number. Basically, this index will tell you about the set number. Okay. And the remaining bits, that is tag. And also remember, the combination, this tag comma index, this complete part, this is called block address. So I can say that this memory address you can divide into two parts. One is block address, another is block offset. Okay. Whatever type of cache memory you take, the main memory address, the physical address, you can divide into two parts. One is block address, another is block offset. So remember, this tag comma index combined, this is called block address. Very simple. Okay, so this is the physical address division in set associative cache. Now let's solve this question. First, we will solve the question number 80. Consider a computer with four-way set associative cache, and these are the characteristics. You can see the main memory size, that is 1 MB. So from here we can find the size of address. So tell me how many bits for address, because already the main memory size is given to you, that is 1 MB. So you can see the memory size. Memory size is given to us, that is 1 MB. 1 MB, that simply means 2 power 20 bytes. Okay, and remember, by default main memory is byte addressable. So every byte has an address. We have 2 power 20 bytes, and every byte has an address. So for address, how many bits we need? 20 bits. Yes or no? So very simple. Here I can say for main memory address, so I can say for physical address or memory address, we need how many bits we need? Address needs 20 bits. Very simple. Okay. Let's see the next. The word size is given to you, that is 1 byte. Let me tell you, by default main memory is byte addressable. So whenever in the question word size is given to you, then don't worry about it, just convert everything to byte. Okay, because by default the main memory is byte addressable. Every byte has an address. For example, here you can see the main memory has 2 power 20 bytes. Every byte has an address. So for address we need 20 bits. Very simple. And word size is 1 byte, and the block size is 128 words. So first you convert this block size to bytes. I'm telling you again that by default the main memory is byte addressable. So whatever data is given to you, for example, block size is 128 words, you convert this to byte. Okay, so here I can say that block size, that is equal to 128 bytes. Why 128 bytes? Because one word equal to 1 byte. So 128 words means 128 bytes. And from here, from the block size, you can easily find the number of bits required for block offset. So for block offset, how many bits we need? That will be, you can see 128, that means 2 power 7. 2 power 7 byte in a block. Within a block, there are 2 power 7 bytes. So if I want to address a byte, a particular byte within this block, if I want to address, then I need 7 bits. Yes or no? So the block size is 2 power 7 byte. So the block offset, that needs 7 bits. Very simple. So we have these 20 bits for address, 7 bits for block offset. We also need to find how many set are there, the number of set, because remember, in the set associative cache memory, the index field means set index. So we need to find how many set are there. So let's find the number of lines first. In the cache memory, how many lines are there? You can see the cache memory size is 8 KB. This is the size of cache memory divided by the line size. Line size is equal to block size. So the block size is basically 128 byte. So this will give me the number of lines. What are the number of lines? BB, that is cancel. So this is 2 power 13. 2 power 13 divided by 2 power 7. So that will be 2 power 6. These many lines are there. And remember, the cache memory is four-way set associative. So how many set will be there? In one set, there are four lines. Total, we have 2 power 6 lines, and one set has four lines. So how many set will be there? So the number of set, that will be 2 power 4. That means 16 set are there. So if the number of set, that is 16, then what is the number of index bits? How many bits we need for set index? So here I can say that for set index we need 4 bits. Okay, because total we have 16 set. That means 2 power 4 set we have. So for set index we need 4 bits. Very simple. Now very easily you can see the address, the complete address, that is basically 20 bits. The address size, physical address size, that is 20 bits. And this address I can divide into 3 parts. For offset, we need 7 bits for offset. We need index bits, and we need 4 bits for index. So for tag, how many bits we need? So very easily you can see for tag we need 20 minus 4 minus 7. These many bits we need for tag. Okay, is this clear? So I can say that for tag we need total 9 bits. Okay, that's it. So this question is asking the number of bits required for tag, set, and word. So the answer will be 9, 4, and 7. Okay, 9, 4, 7. The answer will be option D. Very simple question. Now let's solve this question number 81 in GATE 2008. This question is also basically part of this question. This question number 80 and this question number 81, they are paragraph based question. So let's solve this question number 81 now. The same paragraph is given to us. We have already solved this paragraph. So from this paragraph, we already know that the address, the physical address, the memory address, we can divide into 3 parts. The memory address has total 20 bits. This we have already solved. Okay, this paragraph, from this paragraph, we have already found that for memory address, we need 20 bits. And in the set associative cache, this memory address I can divide into 3 parts: tag, set index, and block offset. So you can see for tag, we need 9 bits. Okay, and you know that for the index, for the set index, we need how many bits? 4 bits. And for offset, we need 7 bits. Okay, this we have already found. Now the question is saying, this question number 81, this is asking that while accessing the memory location, this memory location is given to you. And remember, this H means hexadecimal. Please understand, this H, this suffix H, this means hexadecimal notation, hexadecimal number system. Okay, so it simply means that this number that is given to us, this address, this memory address that is given to us, this is written in the hexadecimal number system. Now the question is saying that CPU has generated this memory location address. And now the question is asking that in this memory location, in this address, what is the tag field? This is what the question is asking. So remember, in the memory address, the most significant 9 bits, that is the tag field. Yes or no? So first you convert this address into binary. Very simple. So this given address, CPU has generated this address 070C795H. Okay, this is the address that is generated by the CPU, and this H simply means hexadecimal. Some people, they also write it 0x, means either you can use this suffix H or you can use this prefix 0x, and then you can write 0C795. Okay, both are same. Now let's convert this to binary. Okay, so if you convert this to binary, then remember it is very simple. From hexadecimal to binary, the conversion is very simple. What we do, every hexadecimal digit, we convert into 4-bit binary number. Okay, every hexadecimal digit we will convert into 4-bit binary number. For example, this 5, In 4-bit binary number, this 5 will be 0101. Okay, this 9, this will be 1001. This 7, this will be 0111. This C means, remember A, B, C means 12. 12 means 1100. And this 0 in 4 bits, this will become 0000. So please understand, converting a hexadecimal number to binary is very easy. Every hexadecimal digit you replace with 4-bit binary number. Every hexadecimal digit you replace with 4-bit binary number. Okay, very simple. And now in this binary address, you can easily find the 9 most significant bits. That will be the tag. Okay, so you can see the 9 most significant bits. Remember, this total is basically 20 bits, and you already know that memory address has 20 bits. Okay, the 20 bits, this is the size of memory address. So this total is basically 20 bits, and in this, the most significant 9 bits, okay, these are the most significant 9 bits. This will be the tag. So the answer will be 0000 Okay, so the answer, what that will be, you can see there are 40, then 11, then there are 30. So for this question, the answer will be option A. Very simple question. I hope you understood. Let's solve GATE 2007 question. Consider a direct mapped cache with 8 cache blocks 0 to 7. So basically, there are total 8 lines in the direct mapped cache. If the main memory block request, these are the block numbers, remember. Okay, these are not the addresses. Okay, because please understand, the CPU will generate a byte address, but in a block you can have many bytes. So the CPU will generate this address, but whenever there is any question related to replacement, always find the block number. Here already the block number is given to you. This sequence, you can see, these are basically block numbers. Okay, these are not the memory addresses, these are block numbers, main memory block numbers. Okay, so if the main memory block requests are in the following order, these are the main memory block numbers that we need to access. Okay, which of the following memory blocks will not be in the cache at the end of the sequence? At the end of this sequence, which of these main memory blocks, these are the block numbers, and which of these will not be present in the cache memory at the end of this sequence? Okay. First of all, let me tell you a note about direct mapped cache. We already know that in a direct mapped cache, for any particular memory block, there is only one possible line, or I can say that every main memory block will map to a unique line. Yes or no? This we already know that in a direct mapped cache, every main memory block will map to a unique line in the cache memory. So there is no choice available, I can say. Yes or no? And that is the reason, remember, in this direct mapped cache, we don't need any replacement policy. We don't need any block replacement algorithm like FIFO, LRU. Okay, these block replacement algorithms we don't need. You can solve this gate. You can see this IIT Delhi question. Which cache mapping function does not require a replacement algorithm? So the answer will be direct mapping. Okay, direct mapping, direct mapped cache does not need any replacement algorithm, any block replacement algorithm. Okay, very simple. Also remember, in this direct mapped cache, if you know the block number in the decimal, then can you find to which cache line that block will map to? We already know that in the direct mapped cache, any block number, any block will map to a unique cache line. So if I give you the block number in decimal, then can you find to which cache line this block will map to? Yes, that is very simple. What we will do? We will use the remainder operator. Okay, basically the block number in decimal, the block number mod the number of lines. This will give me the cache line to which this block will map to. So very simple. Here you can see the cache block means cache line. So the line number I can easily find by this formula, the block number mod number of cache lines. Okay, this will give me the line number to which this main memory block will map to. Very simple. Now, this is a direct mapped cache question, and let me tell you, this type of question, replacement based question in the direct mapped cache, these are actually very simple, because you already know that every block, every main memory block will map to a unique line. So what you can do, when the sequence is given to you, first you find to which line this will map to which line this will map to. For every block you just find to which line they will map to, because every main memory block will map to a unique line. So you just find what is that line number to which this will map to. Okay, very important suggestion I am giving you. It will save a lot of time, that whenever the question is related to direct mapped cache and also related to replacement, okay, we are accessing blocks. You can see this is the block reference, block number request is given to you. In this type of question, for every block number you just directly find to which line number it will map to. So you just write the line numbers also here, to which line number this will map to which line number this will map to, and so on. Okay, and then you can solve this type of question very quickly. So let's find to which line number this block number 3 will map to. That is very simple, 3 mod 8, because the number of lines, you can see the number of cache lines, that is basically 8. Yes or no? Now if I ask you, this block number 3, it will map to which line? You can see this block number 3, it will map to which line? That is very simple, 3 mod 8. So the remainder will be 3. So this is the line number to which this block number 3 will map to. Similarly, I can ask you about 63. If your block number 63, then to which line number it will map to? That is very simple, 63 mod number of lines, that is 8. So the remainder, that is basically 7. Okay, so remember this 7 is the line number. Very simple. So like this you can find for every main memory block, you find to which line number they will map to. So let me quickly write here. You can see this sequence, you can see this is the block number sequence. This is the block number sequence. Now I will be writing the corresponding line number sequence. Okay, so tell me, corresponding to this 3, the line number is also 3. 3 mod 8, the remainder will be 3. For 5, that is also 5, because 5 mod 8, that is equal to 5. Very simple. Next, for this 2, the line number also will be 2. For this 8, the line number will be 0, because 8 mod 8, the remainder will be 0. For this 0, also it will be 0. For 63, it will be 7. For 9, it will be 1. Just divide by 8 and you find the remainder. 16, it will be 0. 20, it will be 4. 17, it will be 1. Correct. Okay, what about 25? 25, it will be 1. Next, what about 18? It will be 2. Okay, just divide by 8 and you find the remainder. These are the line numbers to which these blocks will map to. In the direct mapped cache, every main memory block will map to a unique line. These are those lines to which these main memory blocks will actually map to. Okay, yes or no? What about this 30? Find for this 30 also. Divide by 8 and find the remainder. So for this 30, it will be 6. Okay. What about this 24? It will be 0. For this 2, it will be 2. Okay. For this 63, it will be 7. For 5, it will be 5. For 82, it will be 2. For 17, it will be 1. For 24, it will be 0. Okay, is this clear? So very simple. So this sequence that we got, what is this sequence? This is the line number sequence to which these blocks actually will map to. Okay, now this question has become very simple. You just tell me at the end, in the line number 0, which block will remain. You don't even have to solve now, because remember, you can see at the end, if I ask you in the line number 0, very simple question, these are the lines. Okay, line number 0, line number 1, line number 2, and so on. This is the cache memory, cache data array. Okay, And these are the lines. You can see, for example, this is line 0, this is line 1, and this is line 2, and so on. Okay, so tell me, at the end, in the line number 0, which block will be there? You can see at the end, this block number 24 will be there. That's it. Okay, in this line number 0, block number 24 will be there. Yes or no? Okay, very simple. What about in the line number 1? Which block will be there in the line number 1? You can see in the line number 1, block 17 will be there. Okay, what about line number 2? In line number 2, block 82 will be there. At the end, I am talking about at the end. Okay, yes or no? This is the at the end, this will happen. Okay, what about line number 3? Okay, so let's see. From end, you keep going. From end, can you see 3, 3 anywhere? 3, 3, 3. Yes, 3 we see here. So remember, in 3, in this line number 3, block number 3 will be there. Okay, yes or no? Is this clear? What about line number 4? Okay, just keep going from end. Keep going 4, 4. Okay, just see. Yes, 4 is here. Okay, so that means 20. Yes or no? Block number 20. At the end, in this line number 4, there will be block number 20. Okay, you tell me about line number 5 also. Line number 5, line number 6, line number 7. So this is line 5, line 6, and line 7. Okay, I hope you find this method is actually very time saving. Okay, yes or no? Because this is direct mapped cache, so this method actually you can easily apply for the main memory block reference. For this main memory block sequence, this is the block number sequence. You just find the corresponding line number sequence, and then at the end you can easily find in which line which block will be there. So let's see, what about line number 5? Which block will be there in the line number 5? You can see. Okay, from the end keep going. This is 5. Okay, so that simply means in 5, in this line number 5, the block number 5 will be there. Okay, what about this line number 6? This is line number 6. In this line number 6, you can see from the end keep going. Where are we getting line number 6? Here I am getting the line number 6. Line number 6, that means block number 30. Okay, and what about line number 7? From the end keep going. In the line number 7, which one we got? 63. Yes or no? Okay, so block number 63. So that's it. This is what we have found. Okay, is this clear? Very simple. Okay, so finally, what will be the answer? You can see the question is asking at the end of the sequence, which block will not be there in the cache memory? 3, 18, 20, 30. 3 we have 3, 18, 20, 30. 20 we have, 30 we have, 18 we don't have. Yes or no? So for this question, the answer will be option B. Okay, very simple question. I hope you understood. So this method you can apply in direct mapped question. So let me tell you, I can say note. Whenever the question is related to direct mapped and plus replacement related question. Okay, replacement related question, block replacement related question. So in this type of question, what you can do, the main memory block request, the memory block sequence, the memory block number sequence, if that is given to you, then you convert this to, or I can say you write the corresponding line number sequence. Okay, the main memory block number sequence, if that is given to you, then you convert. Okay, you convert into corresponding line number sequence. Okay, so it will save a lot of time if you do this. Okay, so we have done the complete analysis of this gate question. I hope you understood. One student is asking, suppose in the direct mapped question, the replacement algorithm name is given, then that information is just for confusion. Yes, that's correct. Because in the direct mapped cache, for any memory block, we don't even have a choice. In the direct mapping, any memory block will map to a unique line. So in the question, let's assume somewhere this LRU, FIFO, these words, if these words are given in the question, then also for a direct mapped cache, these words do not matter. Okay, this information is irrelevant because in the direct mapped cache, we don't even have a choice. Any memory block doesn't even have a choice. Every memory block will map to a unique line, so there is no choice available. Okay, that is the reason in the direct mapped cache, the replacement algorithm is not required. Okay, let's solve gate 2005 question. Consider a two-way set associative cache with four set and total number of cache block, that is 8. These are the number of lines, and total we have four set, and in every set there are two lines, and main memory with 128 blocks. What memory blocks will be present in the cache after the following sequence of memory block references? These are the block numbers. These are the main memory block numbers. This sequence is given to us. And the question is asking what memory blocks will be present in the cache at the end of this sequence if we use LRU policy for block replacement, assuming the initial cache doesn't have any memory block from the current job. Means initially the cache memory doesn't have any memory block. Okay, you can assume that initially the cache memory is empty. This is what you can assume. Or I can say that initially you can assume that all the cache lines have valid bit equal to 0. Okay, means initially all the lines they are invalid. Okay, so basically the point is you can assume that initially the cache memory is empty. Okay, this main memory block reference, main memory block number sequence, this is given to us in a set associative cache with LRU replacement policy. So let's solve it. This, let me write this block number sequence. Block number sequence, that is 05 means block number 0, then block number 5, block number 3, block number 9, 0539 7016 and 55. Okay, so these are the block numbers that we are referencing. You can see this in this sequence we are referencing the block numbers. So let's see. Initially, remember, we have two-way set associative cache. Total, we have total number of lines, that is actually 8. And how many set total? Total, you can see we have 4 set. So let me tell you, you have, like for example, set number 0. In this set number 0, there are two lines because the cache memory is two-way set associative. Means in every set there are two lines. Okay, so remember we have set 0, set 1, set 2, and set 3. Okay, and in every set there are two lines. So total we have 8 lines, but there are 4 set. Okay, and remember one more thing. In the set associative cache, to which set a block number will map to? We already know that in a set associative cache, any memory block will map to a unique set. Yes or no? Here we have total 4 set. So tell me, if the block number is given to you in the decimal, like here the block numbers are given to us in the decimal, to which set they will map to? Can we find it? Yes, very easily. Remember, we can find the set number to which a block will map to very easily. What we will do? We will take the block number in the decimal, mod the number of set. The number of set. Okay, so this formula will give me to which set a block number will map to. A block will map to, because remember, in the set associative case, any memory block will map to unique set. Okay, so here we have total 4 set. So what we will do? Any block number in the decimal, these are the block numbers in the decimal, we will divide them by number of set, that is 4, and we will find the remainder. That will be the set to which that block will map to. Okay, very simple. And remember, within a block, you can choose any line. Very simple. And if you want to replace within a block, if you need to replace a line, if you need to replace a cache block, then LRU policy you need to use. The least recently used block you need to replace. Very simple. Okay. So here, first of all, you tell me to which set they will map to. Set number, can you find set numbers? This block number 0, you divide by 4 and you find the remainder. So the remainder also will be 0, means this block number 0 will go to set number 0. This block number 5, 5 divided by 4, the remainder will be 1. So this block number 5, this will go to set number 1. This block number 3 will go to set number 3. Block number 9 will go to set number 1. Because you will divide by 4, the remainder will be 1. Okay, this block number 7 will map to set number 3, set number 0, set number 0. And what about this 55? You divide by 4. So it will be, it will map to, you can see, to set number 3. Yes or no? Very simple. So this is the set numbers to which these blocks will map to. Okay, now let's see. This is our cache memory. This is a 4-way set associative. So let me make 4 set. In every set there are 2 lines. Okay, these are the set 0, set 1, set 2, set 3. Now you can see, initially, first we are accessing this block number 0. It will go to set number 0. So I can put this block number 0 here. So for this block number 0, there will be a miss. And this is a compulsory miss. Why this is a compulsory miss? Because this is the first access to this memory block. The very first access, the very first reference to a memory block, that is a compulsory miss. So this is actually a compulsory miss. Okay, I can write it here that this is actually a compulsory miss. Very simple. Okay, and what about this block number 5? It will go to set number 1. So this block number 5 will go to here. Of course, this is also a miss. Okay, and this is also compulsory miss because this is the very first reference to block number 5. So this is also a compulsory miss. Very simple. What about this block number 3? It will go to set number 3. So in this set number 3, we will put the block number 3. Okay, I can put the block number 3 here. So for this block number 3 also, this is the first reference, the very first reference to any memory block, that is a compulsory miss. So remember, this is also a miss and this is a compulsory miss. The question is not asking you the number of miss. The question is not asking you the compulsory miss or not. Okay, I'm just giving you some extra information in this question. But actually the question is just interested that, okay, at the end of this sequence, which memory block will be present in the cache. Okay, at the end, which main memory blocks will be present in the cache. This is what the question is asking. Okay, so let's see. What about this block number 9? It will go to set number 1. In the set number 1, there is a space. This line is empty. So here I can put this block number 9 also. Okay, so this is also a miss. This is a compulsory miss. What about this block number 7? This block number 7 will go to set number 3. In this set number 3, this line is empty. So here you can put the block number 7. Okay, very simple. And what about this block number 0? It will go to set number 0. In the set number 0, there is a line available. There is a line empty. So here I can put the, actually this is a hit because this block number 0, remember, it is already present in the cache memory. The block number 0, this is already present in the cache memory. This is actually a hit. Okay, remember, this 9 was a miss, compulsory miss. This 7 was a miss, compulsory miss. But this 0 is a hit because when you access this 0, it is already present in the cache memory. So this is actually a hit. Okay, what about this block number 16? This is a miss. This is a compulsory miss because this is the very first reference to block number 16. So this is a compulsory miss. But to which set it will map to? It will map to set number 0. In the set number 0, already this line is empty. So here we can put this block number 16. Very simple. And what about this 55? It will map to set number 3. In the set number 3, every line is occupied. So we need to replace one of the cache blocks with block number 55. And here we need to use the LRU. Okay, is this clear? So remember, for this 55 also there is a miss. This is a compulsory miss. But because this block number 55 will map to this set number 3, in this set number 3 all the lines are occupied. So we need to replace one of the cache blocks in this set number 3. One of the cache blocks I need to replace with this block number 55. And which of them to replace, that decision will be made by the LRU policy, least recently used. So let's see, 3, 7, which is least recently used. See, you are standing here, means you are standing at the request for block number 55. You are standing here. So when you are standing here, then you just see among 3 comma 7, only focus on 3 comma 7, among 3 comma 7, which is least recently used. You can see 7 is used, but 3 is least recently used. Yes or no? So I can say this 3 was actually least recently used. So I will replace this 3 we will replace with 55. Okay, that's it. So at the end, you can see in the cache memory, we have 0, we have 0, 5, 7, 9. Okay, these block numbers you can see 0, 5, 7, 9, 16, 55. Okay, so these block numbers we have in the cache memory at the end. Okay, 0, 5, 7, 9, 16, 55. 0, 5, 7, 9, 16, 55. So the answer will be option C. Okay, very simple question. I hope you understood. Let's solve GATE 2004 question. Consider a fully associative cache memory with 8 cache blocks numbered 0 to 7. Means in this fully associative cache memory, total we have number of lines equal to 8. The following sequence of memory block request. This is the sequence of main memory block numbers. These are the block numbers. These are not the memory addresses. These are the memory block numbers. Okay, you can see block request. If LRU replacement policy is used, which cache block will have memory block 7? Okay, means at the end, this memory block 7, it will be present in which cache block? This is what the question is asking. Okay, so let's solve it. So we have fully associative cache memory, and this is the block request sequence that is given to us. So total we have 8 cache lines. So let me mark all the 8 cache lines. 1, 2, 3, 4, 5, 6, 7. Yes. Okay. So these are the lines. You can see, for example, this is line 0, line 1, line 2, 3, 4, 5, 6, 7. Okay. Now let's see. So this is the memory block number sequence, and we are using LRU replacement policy. One thing to note here, in the fully associative cache memory, any memory block can map to any line. Okay, now the question is asking that at the end, to which cache block will hold the memory block 7? But if you remember one thing, that any memory block can map to any cache line. So for example, this 4, tell me where it will map to? Anyone want to tell me? This memory block 4, to which line it will map to? You might be thinking that it will map to this line number 0, right? But actually, we have a fully associative cache memory. So any memory block, like this memory block 4, it can map to any cache line. Okay, so this memory block 4, you can put in any cache line because it is a fully associative cache memory. Okay, is this clear? So I think in this question, they should mention this information should be given in the question. They should mention that if lines are empty, then we will choose the line with minimum number. Yes or no? This type of information should be given in the question actually. Then this question will become well framed. But now also, of course, we are going to assume the same thing. To solve this question, we are going to assume the same thing, that whenever the lines are empty, then we will choose the line with minimum line number. Yes or no? That type of assumption we will make. But I'm just saying that to make this question well framed, this information should be given in the question. Also, in the question, they should mention that initially all the lines are empty. This information also should be given in this question. In this question, this information also should be given, that at the end of this sequence, because maybe see here, this memory block 7 is here, but let's assume memory block 7 is here also. Okay, let's assume. Then in this question, they should also mention that at the end of this sequence, you answer this question. So basically, I think this question is quite poorly framed. Let me tell you. If you think about this question is not well framed. The question maker did not give you proper information in this question. Of course, you can get the answer, no problem. We will also get the answer. But I am just saying that this is not a well framed question. Some information is missing in this question. Okay, particularly this information that whenever the lines are empty in this fully associative cache memory, if many lines are empty, then for any memory block, we will choose the empty line with minimum number that we will choose. So this type of information they should give in, they should have given in this question, I think. Okay. Anyway, let's solve this question. So this block number 4, it will it can map to any line. So let's put it here. Okay, let's put in the line number 0 this block number 4. What about this block number 3? Let's put it here. Block number 25, let's put it here. Block number 8, block number 19, block number 6, block number 25. That is a hit, please understand. Okay, this block number 25, this will be a hit because already it is available in the cache memory. This block number 25 is already available in the cache memory, so this is a hit. Block number 8, that is also a hit. Block number 16, that is a miss. I can put the block number 16 here. Block number 35, that is a miss. I can put it here. Block number 45, that is a miss. Now I need to replace one of these cache block. Yes or no? So for that we are using the LRU replacement policy. LRU means least recently used. So remember, when you are standing at 45, you are standing here at 45, then you just see which of them is least recently used. Of course, if you go back, you can easily see this 4 was least recently used because remember, after this after this first request, we have never used this block number 4. So this 4 is actually least recently used. So you can replace this with 45. Very simple. Next, what about 22? Is that already present in this cache memory? That is not present. So now you are standing at 22. When you are standing at 22, then tell me, you need to replace one of these cache block, and that will be decided by the LRU policy. So which cache block is actually least recently used? So if you think, if you just go back and you see this block number 3, this is actually least recently used because after this first request to block number 3, we have never used it again. Okay, so this block number 3 I will replace with 22. Very simple. What about this block number 8? That is already a hit, so you don't have to worry. This is a hit. What about block number 3? That is a miss because that is not available in the cache memory, so that is a miss. Now I need to replace one of these cache block. So which is least recently used? You are standing at 3. You go back and you see which is least recently used. Is 25 least recently used? No, 25 is used here also. So actually, if you notice, this 25 is more recently used than this 19. Okay, so let's see. What about this 8? Is this recently used? Yes, this is also recently used. Okay, so the answer actually least recently used will be 19. Yes or no? See, for this request, for this block number, you are standing at this block number 3. I need to replace one of these cache block. So you go back and you see which is least recently used among all these. Okay, among all these blocks, which is least recently used, you can easily notice that this 25, notice 4 is not here, so forget about 4. Okay, forget about 4 because that is not even here. Among these, you see which is least recently used among them. So you can see among them this 25, this is actually used here. Yes or no? We have already reused here this 25. You notice this is reused here. So I can say that the answer actually, or what about 8? 8 is reused here. Okay, so finally, you can easily notice that this 19 is least recently used. So this 19 I will replace with 3. Okay, what about this 16? This is already a hit because it is already present in the cache memory. So this is a hit. Okay, and what about this 25? This is also a hit. This is already present in the cache memory. So this is also a hit. And what about this 7? This is the first reference to block number 7. So for this block number 7, one of these cache block I need to replace. So which is least recently used among them? Okay, so you just go back and you see among them which is the least recently used. So you can see this 6. Yes or no? This block number 6. Because if you notice, after this request, we have never used this 6. So this block number 6, this is least recently used, and I can replace this with 7. So that's it. So you can see at the end, this memory block 7 will be present in which cache line? It is present in cache line 5. Okay, so for this question, the answer will be option B. Is this clear? For this question, the answer will be option B, means the memory block 7 will be present in the line 5. Okay, but there is a problem here in this question. Again, I'm telling you that in this question, because it is fully associative cache memory, so remember, any memory block can map to any line. So for example, if you start that, okay, this 4, if you put here, if you randomly go, if you do it randomly, then of course you will get a different answer. Yes or no? Your answer will not match if you go randomly. For example, let's assume you start, you put this block number 4 in this line number 3, this block number 3 you put here, this block number 25 you will put here, like that. Okay, if you go randomly, then remember, then for this question the answer will not match. Okay, you will not get the correct answer. And this is a mistake of not yours. This is a mistake of this question, the question maker. The question maker should mention this information in this question. Okay, one more thing, let me tell you, because this information is not given in the question, so can I say it will be marks to all? This information, you can see, it is not available in this question, so can I say it will be marks to all? No, it will not be marks to all, because remember, whenever the algorithm, see, from the algorithm point of view, this LRU algorithm or whatever algorithm you take, from the algorithm point of view, some order we will use. Do you agree with me? In the algorithm, we will not say that, okay, randomly put anywhere. To the algorithm, we will say that if some lines are empty, then choose the line with minimum number. Do you agree with me? Yes or no? So please understand that in this question, it will not be marks to all. To solve this question, you need to follow this order, that if some lines are empty, like let's assume these lines are empty, then for any new memory block, you choose the line with minimum number, because this is what the algorithm will do. Algorithm will not randomly put that, okay, randomly you are putting 4 here, 3 here, 25 here. No, not like that. Algorithm will go in a systematic way. Okay, it will do like this: first 4 here, then 3 here, then 25 here, like this. In a systematic way it will go. So this question will not become marks to all, but this question is a very poorly framed question. This is what I am saying. I hope you understood. Let's solve gate 2025 question. For a direct mapped cache, 4 bits are used for tag field, 12 bits are used for index into cache block. Because remember, in a direct mapped cache, the index bits, these, they will basically tell you the line index. Yes or no? In the direct mapped cache, the index bits are the line index, or I can say they will tell you about the line number. That is the reason this statement is given, that 12 bits are used for index into cache block, means index into cache line. In the set associative cache, we will say that index into cache set. Yes or no? If the same question is for set associative cache, then here we will say index into cache set. But in the direct mapped cache, we will say index into cache block. Okay. The size of each cache block is 1 byte. Assume there is no other information stored in any cache block. What it means, can anyone tell me? This line, read this line. Assume that there is no other information stored in each cache block. What this means? Does it mean that tag is also not stored? Does it mean? No, tag must be stored. Tag will always be stored. It cannot happen that tag will not be stored. This line simply means that we don't have additional bits like valid bit, dirty bit, LRU information, something like that. Okay, so please understand what this line means. Assume that there is no other information stored for each cache block. What this line means? This line simply means that only tag is stored, no other status bit like valid bit, dirty bit, something like this. Okay, so remember, this simply means only tag is stored, only tag comma block. Okay, memory block, only these are stored. Okay, we will store this tag in the tag directory that you already know. This tag will be stored in the tag directory. Okay, and remember, this block will be stored in data array. But the point is that only tag comma block these are stored, no valid bit, etc. Okay, no extra bits are there. I hope you understood this statement. Now, the question is asking which one of the following is correct option for the sizes of main memory and the size of cache memory. And the system is byte addressable, means for every byte there is an address. Tell me one thing, the question is asking the size of cache memory. When we ask the size of cache memory, then does it include the tag directory size? Tell me. Very simple question. The question is actually asking the size of cache memory. You can see the correct size of main memory and the correct size of cache memory. So when we discuss the size of cache memory, does it include the size of tag directory? The answer is no. Remember, cache memory consists of data array and tag array. In the tag array, we store the tag and also the valid bit, dirty bit, basically the status bits we store in the tag directory. This tag array, this is also called tag directory. Here we store the metadata, the extra data, okay, like the tags and all. And in this data array, here we store the block that we fetch from the main memory. Okay, so remember, when we discuss the size of cache memory, then we only consider the size of data array, means the number of lines multiplied by the size of a line. Remember, when we discuss the size of cache memory, then we do not include the size of tag directory unless it is said in the question. If explicitly it is given that okay, you need to include the tag directory size also, then only we will include. Means in the question, if it is given that we need to include the tag directory size also in the total cache memory size, then we will include this tag array size. Otherwise, we will never include the tag array size in the size of cache memory. Okay, so here you can see in this question, we need to find the size of cache memory. That simply means the number of cache lines multiplied by the line size. This will be the answer for this. Okay, is this clear? Very simple. Also remember, we have a direct mapped cache. In a direct mapped cache, the physical address, the main memory address, we can divide into three parts: tag, index, and offset. This offset will be the block offset. This you can find from the block size. And remember this index, this will be the line index. Means in the direct mapped cache, this index actually will tell you the line number, because remember, in a direct mapped cache, any memory block will map to a unique line. That is the reason this index means line index. It will tell you about the line number. Okay, also one more thing, remember, this tag comma index, this combine, this is your block address. So whatever cache memory you take, whatever type of cache memory you take, direct mapped, set associative, fully associative, always remember that the main memory address, the physical address, you can divide into two parts. One is block address, another is block offset. So you can easily see this tag comma index, this combination combined, this is actually your block address. So remember, this area, this is your, this field, this is your block address, this is block offset. In any type of cache memory, the physical address you can divide into two parts: block address, block offset. Very simple. Okay, now let's solve this question. So here you can see that in a direct mapped cache, 4 bits are used for tag field and 12 bits are used for index. 12 bits are used for index. So you tell me, if 12 bits are used for index, then how many lines are there? Can you tell me? You can see for index how many bits are used? 12 bits. 12 bits are used for index. And you already know that this index means line index. In the direct mapped cache, index means line index. This will tell you about the line number. So for index, if you have 12 bits, it means what are the number of lines? That will be 2 power 12. These many lines are there in the cache memory. And what is the line size? the size of each cache block, that is 1 byte. So what will be the cache memory size? Tell me, what will be the cache size? That will be number of lines multiplied by line size. Line size is only 1 byte. So the answer will be what? That will be 4 KB. This will be the answer. Very simple. This is the cache memory size. And what about main memory size? You find for main memory address how many bits we need. That is what you find. Already remember, we know that the main memory address we can divide into three parts: tag, index, and offset. Yes or no? This is the main memory address. This is the memory address. I can divide into three parts: tag, index, and offset. And for tag, you can see 4 bits are required. 4 bits for tag. This is the tag. Okay, and for index, for line index, the question has given that 12 bits are required for line index. And what about offset? How many bits are required for offset? The block size is given to you, that is 1 byte. Please understand one thing, that if the block size is, see, if the block size is, let's assume 2 power k bytes, then how many bits we need for block offset? For block offset, if the block size is 2 power k bytes, then for block offset we need k bits. Okay, and in this question the block size is given to you, that is 1 byte. What that means? That means 2 power 0 byte. So if the block size is 2 power 0 byte, then for block offset how many bits we need? For block offset, number of bits required, how many bits we need? That will be 0. Yes or no? When the block size is 2 power k bytes, then for block offset we need k bits. K bits. You can see if the block size is 1 byte, means 2 power 0 byte, then for block offset number of bits required, that will be 0. Means what it means? It means there is no block offset. It means there is no block offset. Okay, is this clear? So remember, when the block size is 1 byte, then it simply means there is no block offset. Okay, that's it. So here I can say that none. Here I can say none. Okay, there is no block offset. So here I can say none. So finally, main memory address size. What is that? Main memory address needs how many bits? That will be 12 plus 4. That will be 16 bits. Okay, so in the main memory there are, for address we need 16 bits. And remember, by default the main memory is byte addressable, and that is given in the question that it is byte addressable. Means on every address there is a byte. Yes or no? So tell me, how many total bytes are there? For address we need 16 bits, and on every address there is a byte. So what is the size? What the I can say memory size? Memory size, that will be equal to 2 power 16 bytes. Yes or no? Because remember, for address we need 16 bits. So 16 bits, that simply means 2 power 16 locations. And because the main memory is byte addressable, so on every address there is a byte. So on every location there is a byte. So that is the reason main memory size, that will be 2 power 16 bytes. 2 power 16 bytes, that simply means 64 KB. That will be your answer. So the main memory size 64 KB and the cache memory size 4 KB. The answer will be option A. Very simple question. I hope you understood. One student is asking, repeat memory address bits. Means how many bits we need for memory address. Let me repeat. We already know that in the direct mapped cache, the main memory address we can divide into three parts. Yes or no? Correct. That we already know. The main memory address, this is the main memory address. This memory address we can divide into three parts in the direct mapped cache. And these three parts we already know. These are tag, index, and offset. Index means line index. In the direct mapped cache, index means line index. Okay, already the question has given you the size of tag. The question is saying that 4 bits are used for tag. This line is given in the question. Okay, so I can say that 4 bits we need for tag. For index, in the question it is saying that 12 bits for index. You can see this line is given in the question. 12 bits, 12 bits are used for index. Okay. And already we have seen that there is no offset field, none. What is the reason? Because the block size is only 1 byte. This is given in the question that block size is 1 byte, and because block size is 1 byte, 1 byte means 2 power 0 byte. That is the reason for block offset we need 0 bit, means there is no bit required for block offset. Is this clear? So I can say there is no bit required. We have no bit. There is no bit required for offset. Okay, so you can see there is none. I can say. So tell me now, total main memory address bits. How many bits I need for main memory address? That will be 4 plus 12. So that will be 16 bits. Is this clear? Very simple. And remember, the main memory is byte addressable. This is given in the question that it is byte addressable. And if it is not given, then also we need to assume by default the main memory is byte addressable. Okay, so here you can see that total memory address needs 16 bits. 16 bits means total we have 2 power 16 locations in the main memory. Yes or no? This is the main memory, and you can see for address we need 16 bits. 16 bits, that simply means total we have 2 power 16 locations. Yes, correct? Okay, locations. Total we have 2 power 16 locations. And because the main memory is byte addressable, so on every location there is a byte. Every byte has a address, I can say. Okay, so on every location there is a byte. So now you tell me what will be the main memory size? The main memory size that will be equal to 2 power 16 bytes. Is this point clear? Very simple question. Let's all get 2025 question. Consider a memory system with 1 megabytes of main memory, 16 kilobytes of cache memory. Assume that the processor generates 20-bit memory address. The cache block size, that is 16 bytes. If the cache uses direct mapping, we have a direct mapped cache. How many bits will be required to store all the tag values? Assume that the main memory is byte addressable. 1K means 2 power 10, 1M means 2 power 20. The question is asking how many bits will be required to store all the tag values. Let me tell you, first of all, in a direct mapped cache, the main memory address you can divide into three parts that we already know. So you can see the physical address division in the direct mapped cache. This physical address, the main memory address, I can divide into three parts: tag, index, and offset. Offset means block offset. This you can find from the block size. Index means line index. This you can find from the number of lines. How many lines are there in the direct mapped cache? Remember, in the direct mapped cache, index means line index, and the remaining bits, these are the tag. Also remember that this tag comma index, this complete part, this is called block address. So I can say that physical address you can divide into two parts: block address, block offset. Very simple. Also remember, the question is asking how many bits are required to store all the tag values. Where do we store the tag values? Do you know? So let me tell you that cache memory consists of two parts. One is data array, another is tag array. In the cache memory there are two parts. One is data array, tag array, and in this tag array we store the tag bits. In this tag array we store the tag bits. We also store the valid bit, dirty bit, and other status bit. So remember, in this tag array this is a physical storage, and this data array, that is also a physical storage. In this data array we store the block that we fetch from the main memory. So the actual data we put in the data array, and in this tag array we store the tag. Also we store the status bit like valid bit, dirty bit, like that. Okay, so you can see this. You can see cache memory consists of data array and tag array. This tag array, this is also called tag directory, and in this tag directory we store the tag bits associated with each cache line. Okay, remember, this is a separate physical storage from the cache data array. There is a cache data array. In this cache data array we store the actual blocks that we fetch from the main memory. Okay, basically the actual data we store in the cache data array. But in the tag array, in the tag directory, we store the extra data, the metadata, like we store the tags, we store the status bit, like valid bit, dirty bit, LRU information, like that. Okay. And when we say cache memory size, in the cache memory size, we do not include the tag directory size. We only find the data array size. Means cache memory size is equal to data array size. Okay. But in this question, they are explicitly asking you that how many bits will be required to store all the tag values. Means the question is asking you that in this tag array, we store the tags. Yes or no? For every cache line, we store a corresponding tag. With every cache line, we store a corresponding tag. So in this tag array, we are storing the tag values. Now the question is asking total how many bits will be required to store all the tag values. So what we need to do? You need to find corresponding to one cache line how many tag bits are required, and then you multiply with the number of cache lines. Yes or no? Very simple. So total number of tag bits that we need to store in the cache memory. See, remember, this is the cache memory. In this cache memory, there are two parts: tag directory and data array. So remember, question is asking that in this entire cache memory, how many bits are required to store all the tag values. So what you do? Corresponding to one cache line, how many tag bits we need? Okay. So how many tag bits we need to store corresponding to one cache line, multiply with number of cache line. That will be the total number of bits required to store all the tag values. Very simple. Okay. So here you find what is the number of lines. First you find that. So let's find the number of lines. It is a direct mapped cache, and we have what is the cache memory size? 16 KB. Okay, this is the cache memory size. You can see 16 KB of cache memory divided by what is the line size? Means block size. The cache block size, that is 16 bytes. So what will be the number of lines? That will be 1K lines. That means 2 power 10 lines are there. Okay, very simple. So we have these many lines. Now we need to find corresponding to every line how many tag bits we need. So you see in an address how many tag bits are required, because in a direct mapped cache, the memory address, the physical address, you can divide into three parts. Okay, and you can see these are the three parts: tag, index, and offset. This index means line index. Remember, if you have 2 power 10 lines, then for index you need 10 bits. And the cache memory block size, that is 16 byte. So for offset you need 4 bits. Okay, very simple. And what is this main memory address size? How many bits are required for main memory address? That is given to you, that is 20-bit memory address. So this total is actually 20 bit. So for tag, how many bits I need for tag? That will be only 6 bits. Yes or no? We need 6 bits for tag. So please understand that corresponding to every line, like this is your data array, this is your data array. Okay, in this data array, there are lines. Yes or no? For example, this is line 0. These are the lines. Line 0, line 1, and so on. And you already know that corresponding to every line in the tag directory, there is a tag directory. Okay, so this is tag directory, or I can say tag array. In the tag array, remember, corresponding to every line, we store a tag. So we store a tag here. Okay, corresponding to every line, we store tag. So please understand, this is basically your tag bits. Okay, is this clear? So now you can easily see total how many bits are required to store all the tag values. That will be equal to number of lines, that is 2 power 10, 2 power 10 lines. Yes or no? So number of lines multiplied by corresponding to one line, how many tag bits I need to store? 6 tag bits I need to store. Yes or no? 6 tag bits per line. 6 tag bits per line. Okay, for one line, 6 tag bits I need to store. Total we have 2 power 10 lines. So finally, what are the number of tag bits? That will be 6 into 2 power 10. This will be the total tag bits. In the cache memory, this is the total number of bits required to store all the tag values. So the answer will be 6 into 2 power 10. Option A is the answer. Very simple question. Let's solve GATE 2023. A 8-way set associative cache. Let's solve GATE 2023 question. 8-way set associative cache of size 64 KB. 1 KB means 1024 bytes, means 1 KB means 2 power 10 bytes. So this set associative cache is used in a system with 32-bit address. The address is subdivided into tag, index, and block offset. In a set associative cache, this index means set index. This will tell you about the set number. In a set associative cache, in the direct mapped cache, index means line index, but here it is set index. Yes or no? The number of bits required for tag. This is very simple. You find the block size is given to you, so you can find the number of bits required for block offset. The block size, that is that given 8-way set associative cache of size 64 KB, 32-bit address. Let's all get 2023 question. 8-way set associative cache with size. The cache memory size, that is 64 KB. 1 KB means 1024 bytes, means 1 KB means 2 power 10 bytes. And the system has 32-bit address. The address is subdivided into tag, index, and block offset. We already know in a set associative cache, the memory address, the physical address, we can divide into three parts: tag, index, and block offset. This index means set index. Okay, in the set associative cache, this index means set index. So if you know the number of set, then you can easily find the number of index bits needed. Okay, and this block offset you can find from the size of block, from the block size. The question is asking the number of bits in the tag field. In this question, notice that the block size is not given to you. Okay, I told you that when you break the address into three parts, the physical address you can break into three parts: tag, index, and offset. Then first you find the number of bits required for offset, then you find the number of bits required for index, and then you find the number of bits required for tag. So if I want to find the number of bits required for tag, first I need the number of bits required for block offset, and for that I need the block size. That is not given in the question, so we can assume. Okay, yes or no? Let's assume for a moment that block size, let's assume that block size is 2 power m bytes. Okay, this is the block size, let's assume. So now you tell me, for block offset, how many bits we need? How many bits we need for block offset? That will be m bits. Okay, we are assuming that block size is equal to 2 power m bytes. So for block offset we need m bits. Very simple. Now we already know that the physical address, the size of address, that is 32-bit. Okay, so you can see the total is 32 bits, this total. And this I can subdivide into three parts, and these parts you already know: tag, index. Index means set index, and offset. So for offset we need m bits. Okay, now we need to find how many bits we need for index. Index means set index. Okay, so we need to find the number of set in this set associative cache. So first you find the number of lines. What will be the number of lines? Let me find on the next page. So first you find the number of lines in the cache memory. And how to find the number of lines in the cache memory? Cache size divided by the size of line, the line size. So I can say the cache memory size, that is 64 KB. This is the cache memory size, divided by the line size, that is 2 power m bytes. So from here you can see BB cancel. So it will be 2 power 16 divided by 2 power m. It will be 2 power 16 minus m. This is the number of lines. Now we need to find the number of set, because in a set associative cache memory, the index means set index. So to find the number of bits required for set index, we need to find how many set are there. So let's find the number of set. That will be number of lines. This is the number of lines. You can see these many lines we have. So the number of lines divided by In one set, there are 8 lines, because you can see the set associative cache memory. This is 8-way set associative cache memory. So in one set, there are 8 lines. Total, we have these many lines. In one set, there are 8 lines. So here you can see it will be 2 power 16 minus m minus 3. This is the number of set. These many sets are there. So from this number of set, you can easily find for set index how many bits we need. For set index, I need 16 minus m minus 3. These many bits we need for set index. Okay. So that's it. For set index, we need 16 minus 3 minus m. These many bits we need for set index. And the remaining bits will be needed for tag. So you can see for tag how many bits we need. That will be 32 minus m minus this value. Okay. So you can easily see number of bits, number of tag bits, that will be equal to 32 minus m minus 16 minus 3 minus m. Okay, so finally here you can see it will be 32 minus m minus 16 plus 3 plus m. So minus m plus m, they will cancel, and finally you will get 32 minus 13, or I can say 32 minus 16, that is 16, that is 16 plus 3, that is 19. So 19 bits. So that's it. So for this question, the number of bits required for tag, that will be 19 bits. Okay, very simple. I hope you understood this. If you want a general formula, that also we can derive, but you don't need to remember that general formula. Okay, so let me derive a general formula. Let's derive a general formula for tag bits in set associative cache. Okay. Let me give you this question in a weekly quiz. Same data I will give you, the same data that is given in this 2023 question, the same data I will give you. Okay, but instead of this 8-way, I will give you 2 power k. Here I will give you something 2 power a, 2 power b, something like that. So abstract data I will give you, and then I will ask you the number of bits required for tag in a set associative cache memory. So you can derive it. The same way we have done this question, the same way you can do that question also. Okay. So this derivation of general formula you can do yourself. Okay, and I will put a question in the weekly quiz. Remember, the method is same. Okay, as we have done this gate 2023 question, the same way you can do this I can say this abstract question also. Okay, now let's move on. Let's all get 2022 question. Consider a system with 2 KB direct mapped cache, data cache, with a block size of 64 bytes. The system has a physical address space of 64 KB and word length of 16 bits. During the execution of a program, 4 data words PQRS are accessed. Remember, the word size is 16 bits, means 2 byte. And these PQRS, these are data words, means P has 2 bytes, Q is 2 byte, and R, O, and S, they are also basically 2 byte data words. Okay. These are not block numbers. Please understand. PQRS, these are not block numbers. These are words. You can see. The question is saying during the execution of a program, 4 data words PQRS are accessed in that order 10 times. PQRS, 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 and so on. Hence, there are 40 access to data cache altogether. Assume that data cache is initially empty and no other data words are accessed by the program. The program only accesses PQRS in this order 40 times. The program only accesses these 4 words PQRS, 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 like that 10 times. You can see total 40 access are there. There is no other word, no other data word is accessed by the program. The addresses of the first bytes of PQRS, these are the addresses of first bytes of PQRS. For the execution of the above program, which of the following statements are true with respect to the data cache? The four statements are given to you. Every access to S is a hit. Once P is brought to the cache, it will never be evicted. At the end of the execution, only R, S reside in the cache. Every access to R evicts Q from the cache memory. So, see, this is very simple question. Let me tell you. First of all, here you have direct mapped cache. In a direct mapped cache, every memory block will map to unique line. Yes or no? The second thing, this question is related to replacement, block replacement. Yes or no? So you can see PQRS, 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 like that. Program is accessing four words PQRS. But remember, these PQRS, these are not blocks. So whenever there is any question related to block replacement, first you find the block numbers. Okay, here remember these data words are given to you, but please understand these are not blocks like P, Q, R, S. They are not block numbers. P is not a block number. P is part of some block. Okay, like this is a block and P is part of some block. So P is not a block number. So for this PQRS, we first we will find to which block they belong to. Yes or no? Is this clear? Whenever there is any question related to block replacement, then always find the block numbers. Okay, so from this PQRS, because these are not blocks, these are words, these are data words. From them, we will find to which block they belong to. That is the first thing that we will do. Okay, many students, the mistake they will make, they will assume that PQRS, they will think that PQRS are data blocks. Okay, yes or no? They will assume that these are block numbers. P is a block number, Q is a block number, and like this. But actually, they are not block numbers. Okay. Also, let me tell you that because this is direct mapped cache, in a direct mapped cache, the physical address, the memory address, we can divide into three parts: tag, index, and offset. Index means line index. In a direct mapped cache, index means line index. In a set associative cache, index means set index. Also remember, in a direct mapped cache or in any type of cache memory, the main memory address you can divide into two parts: block address, block offset. So please understand that this tag comma index, this combination, this combined part, this is actually block address. You can see in this diagram here that this tag comma index, this is actually block address. So if you want to find the block address, then that will be tag comma index combination. This is the block address. The physical address in any type of cache memory, whether you take direct mapped, fully associative, set associative, in any type of cache memory, the physical address we can divide into two parts: block address, block offset. Okay, you can see this here. This is a general note from the previous lecture, from our lectures, cache memory lectures, that for any type of cache memory, the main memory address consists two parts. The most significant part indicates the block address or block number, and the least significant part indicates the block size or block offset. So you can see in this diagram here that the address, the memory address, the byte address, because the CPU will generate a byte address. By default, main memory is byte addressable. So for every byte, there is an address. So when the CPU will generate address, on that address, you will find a byte. Yes or no? So you can see this is the address generated by the CPU, means this is the main memory address, or I can say physical address, or I can say byte address. This you can divide into two parts: block address and block offset. Okay, very simple. Now let's solve this question. First, notice that what is this PQRS? These are 2 bytes word. Okay, read everything one by one. You can see that word length is equal to 16 bits. So one word is equal to 2 2 bytes. That is the first thing. Okay, the second thing you can notice that these are 4 data words. Okay, PQRS, these are the data words. So it simply means that P is a word. Okay, in this P there are 2 bytes. See, this is P, but in this P there are 2 bytes. And the question is saying, you can see the question is saying that the address of the first byte of P, that is 0xA248. So remember, this is the first byte, this is the second byte. So you can see the address of the first byte. What is that address? In the hexadecimal, 0x prefix, that means hexadecimal. So 0xA248. This is the address of the first byte of this word P. Is this point clear? Also remember one more thing, that this P is not a block. So basically there is a block. What are the block size given to you in this? The block size is, you can see, 64 bytes. This is given in the question. So remember, this is a block. This is a block, and this has 64 bytes. Inside this block, there are 64 bytes. And remember, inside this block, there is P. Is this clear? Inside this block, there is, this is P. Similarly, this Q also belongs to some block. R also belongs to some block. S also belongs to some block. So please understand, very important note, that PQRS are not block numbers. PQRS are not block numbers. So first we need to find the block numbers from PQRS. Okay, is this clear? Because all these PQRS, they actually belong to some block. This is some block. This is a block, and inside this block, this Q is there, and Q has 2 bytes. This Q has 2 bytes. Very simple point. Okay, and in this block there are 64 bytes are there total, but this Q has only 2 bytes. Very simple. So PQRS, these are not block numbers. So from PQRS, first we will find the block numbers. First find block numbers to which they belong to. Block numbers to which they belong to. Okay. Now let's find the block numbers to which they will belong to. But before that, let's do the address division. You can see we have 2 KB cache memory, direct mapped cache. Okay, 2 KB direct mapped cache we have. Also, the block size is equal to line size. We already know block size is 64 bytes. Okay, next, the address space, the physical address space is 64 KB. So the main memory size is given to you. Memory size, that is 64 KB. You can see the physical address space is 64 KB. So means the main memory size, that is actually 64 KB. And remember, the main memory, is this byte addressable or word addressable? Can anyone tell me? The main memory, is it byte addressable? Is it word addressable? It is byte addressable. By default, the main memory is always byte addressable. If nothing is given to you in the question, whether the memory is byte addressable or word addressable, then always remember that main memory by default, that is always byte addressable. In the question, if they mention, a line is given to you that main memory is word addressable, if this statement is not given in the question, then always assume that main memory is byte addressable. Okay, some students, what they do, when they see the word, this word, okay, in the question, when they see this terminology, word length, then immediately they think that, okay, the main memory is word addressable. No, remember, in a byte addressable also there is word. Yes or no? If your main memory is byte addressable, then also the word size can be anything. For example, in your computer, okay, right now, this, in my computer, you can see in your computer also, the main memory is byte addressable, but one word size is equal to 64 bytes, 32 bytes. So remember, in the question, if word size is given to you, it does not mean that main memory is word addressable. Some students, when they see the word size in the question, then immediately they think that, okay, the main memory is word addressable. No, the main memory is always byte addressable, unless in the question, if they mention that, okay, the main memory is word addressable. I hope this point is clear. You can see, you can read in this question, this information is not given whether the main memory is byte addressable or word addressable. This information is not given, so we will assume that main memory is byte addressable. Okay, I hope this point is clear. So don't confuse. So you can see the main memory size, that is 64 KB. So from here, you tell me how many bits we need for address. For address, how many bits we need? You can see 64 KB. That simply means 2 power 16 bytes. This is the main memory size, 2 power 16 bytes. So for address, we need 16 bits. Very simple. Okay. And let me also write it here, by default byte addressable. Okay. Now you can see the address has 16 bits total. This address has 16 bits. This is the address. And this you can divide into three parts: tag, offset, index. Okay. So you can see for index, how many bits we need? That will depend on the number of lines. Tell me how many lines are there? Number of lines, that will be the cache memory size. 2 KB is the cache memory size divided by the line size, that is 64 bytes. So here you can see it will be 2 power 11 divided by 2 power 6, so that will be 2 power 5. These many lines are there. Okay, so for line index in the direct mapped cache, index means line index, yes or no? So this is line index. For line index we need 5 bits. Okay, and for offset you can see the block size is 64 bytes. So for offset, for block offset, how many bits we need? That will be 6 bits. So we need 6 bits for block offset. And how many bits are required for tag? You can see the remaining number of bits, that means 5 bits are required for tag. Okay, this is the division of physical address. This is the division of main memory address, very simple. Now let's see the next step. Now we will find this PQRS, these words, they belong to which block? Yes or no? So here you can see this P. This P belongs to which block? Let's find block number containing P. Containing word P. Okay, P is a word. So very simple. We just want to find that, okay, in which block? This is the block. The block size is 64 bytes, that we know. Okay, so you can see in this block there is P, and P has 2 bytes. So this is P. Very simple. And remember the address of first byte of P that is given to you. What is that? This is P. And in this P, remember the address of first byte. This address is given to us, that is in the hexadecimal A248. Okay, in the hexadecimal A248. Very simple. So you can see this is the address of the first byte of word P. Let me convert this to binary. Converting a hexadecimal address to binary, that is very easy. What we will do, every hexadecimal digit we will replace with 4-bit binary number. Yes or no? This is how you can convert hexadecimal number to binary number. This hexadecimal address to binary address you can easily convert. Every hexadecimal digit we will replace with 4-bit binary number. This 8 we will replace with 1000. This 4 we will replace with 0100. This 2 we will replace with 0010. And this A means 10. A we will replace with 1010. Okay, notice how many bits are there? Total we have 16 bits, because we have already seen that memory address has 16 bits. Yes or no? This we have already found, that main memory address has 16 bits. So you can see total we have 16 bits. Okay, now tell me how to find the block number here. We want to find the block number containing P. So tell me how to find the block number here. I told you that address you can divide into two parts, block address and block offset. This I told you, that the address that you have, this memory address that you have, this you can divide into two parts. Okay, those two parts, these are basically offset, block offset, and block address. Block offset and block address. Okay, so here also you can easily see that we can divide this address into two parts, block offset and block address. You can see for block offset we need 6 bits for block offset. Okay, so the least significant 6 bits, these are basically for block offset. These are for block offset. Okay, this is for block offset. And remember, the most significant, the remaining number of bits, this this is for block address. This is your block address, or I can say block number. Either you can call it block address or you can call it block number. Very simple point. So tell me, to which block P belongs to? Let me know. So you can see block number or block address containing P. What that will be? That will be 1010 0010 01. Okay, is this clear? This will be the block address containing P. I hope you understood. So this is just for understanding purpose. I have done this, but now let me do it very quickly for PQRS. Okay, for all of them. So you can see that P was basically 0x A248. A248. This is P. What about Q? Q was 0x C28A. C28A. Okay, PQRS. What about R? You can see R is CA8A. 0x CA8A. And what about S? That is A262. A262. Okay, these are the addresses of the first byte of PQRS. These are the addresses of the first byte of PQRS. Okay, so from here, from these addresses, or I can say these are the addresses of PQRS basically. Okay, P has 2 bytes because P is a word, Q is a word, one word equal to 2 bytes. So we just want to find to which block number they belong to, this PQRS, to which blocks they belong to. Okay, so that we can easily find from these addresses. These are the addresses of PQRS. This is the address of Q. This is the address of R, and so on. So let's see what we will do. We will write this in the binary. Okay, so this A means 1010. This is A. 2 means 0010. This is 2. 4 means 0100. And 8 means 1000. What about this Q in binary? C means 1100. C means 12. 12 means 1100. How to convert this hexadecimal address to binary address? Every hexadecimal digit we will replace with corresponding 4-bit binary number. So you can see this 2 means 0010, 8 means 1000, A means 1010. Okay, what about this CA8A? C means 1100, A means 1010, 8 means 1000, A means 1010. What about this S? This A means 1010, 2 means 0010, 6 means 0110, and 4 means 0100. Okay, is this clear? Now, very easily you can see that the least significant 6 bits, these are the offset. Yes or no? The least significant 6 bits, this is the offset. This is the offset. Okay, so let me draw a line here. The least significant 6 bits, that is the offset. In all of them, the least significant 6 bits, these are offset. Is this clear? These are block offset. This is also block offset. Okay, these are basically offset. And what about the remaining bits? Tell me. The remaining bits, that is the block address. Is this clear? The remaining bits, you can see this is the block address, the block to which this P belongs to. Okay, is this clear? Block address or block number, the block to which this Q belongs to. This is the block address. Similarly here, this is the block address. Okay, and here also you can see this is the block address. I hope you understood this. So now you tell me, is there any two of them which belong to the same block? Tell me. PQRS, look at their block addresses. because you can see this P belongs to this block, Q belongs to this block, R belongs to this block, and S belongs to this block. So notice one thing, P comma S, they belong to same block. Did you notice? 1010 001001. Here also 1010 001001. Did you notice that P comma S, they belong to same block? Okay, but notice the others, Q belongs to some other block, R belongs to some other block. So basically there are three blocks. Do you agree with me? So what we have seen that P comma S, they belong to same block. Like this is your block. Okay, this is a block. And what is its address? What are the this is a block whose address? What is the block address? Let me write, or I can say block number. So what are the block number or block address? That is basically 1010 in binary, 001010. Okay, sorry, 001001. So you can see that this is a block whose block address is this. This is the block address. And let me tell you that inside this block, actually there are total 64 bytes. Okay, inside this block, there are 64 bytes. But also you can notice P comma S, they are present inside this block. Okay, is this clear? You can see P is this offset. This offset will tell you where P is present, and this offset will tell you where Q is present. So you can see P is present before Q. Yes or no? From this offset, this value is smaller than this value. Here you have 001000. Here you have 100100. So you can easily notice that somewhere here P is present. Okay, somewhere here P is present. P has 2 bytes, but somewhere here P is present, and somewhere here Q is present. Sorry, S is present. Somewhere here S is present. Okay, is this clear? Understood? And similarly, remember that Q comma R, P comma S, they belong to same block, but the remaining, you can see Q belongs to some other block. Okay, Q is here, some other block, and R is here, some other block. Okay, is this clear? I hope you understood. So let me say that, for example, you can say that this is your block of PQ. Okay, this is the block containing P comma Q. Sorry, P comma S. You can think like this, that this is block of PS. Means this is the block containing P comma S. Okay, you can assume that this is like block of Q, block containing Q, and you can assume this is like block containing R. Okay, is this point clear? Very simple. Agree? Now let's see one thing. The program is accessing PQRS like that 10 times. Yes or no? You can see the access sequence is given to you. What is that? That is like PQRS, then PQRS, then PQRS, like that. Okay, and so on. But notice one thing. Just tell me one thing. If P is present and we refer S, then there is a hit or miss. Tell me. In the cache memory, let's assume P is present. Means that block is present which contains P. Now, if we access S, then there will be hit or miss. There will be hit because S also belongs to the same block. Yes or no? Is this point clear? Very simple. Now, remember, we already know that P comma S, they belong to same block. That is fine. P comma S are in the same block. But to which line they will map to? We are talking about direct mapped cache. In a direct mapped cache, every memory block will map to a unique line. Okay. So you can easily notice that the least significant 6 bits, these are offset. And what is the number of index bits? We have already seen the number of index bits. That is 5 bits. Okay. And 5 bits for tag. So please understand that here, these 5 bits, these 5 bits are for index, line index. These are for line index. Means to which line the block containing P will map to. Okay, is this clear? Similarly, remember to which line the block containing Q will map to, and to which line the block containing R will map to, and to which line the block containing S will map to. Is this clear? These are the line index. Okay, is this clear? Means the block containing Q will map to this line number, and the block containing R will map to this line number. The block containing S will map to this line number, and the block containing P will map to this line number. Of course, P comma S, they belong to same block, so they will map to same line. You can easily notice this line index and this line index are same because P comma S belong to same block, same memory block, so they will map to same line. So that is the reason you can easily see this line index here. Okay, let me do this. That you can notice that this line index here and this line index here, they are basically same. Okay, of course this is very simple point because P comma S, they belong to same memory block, so they will map to same line. Okay, but notice one more thing: Q comma R, they belong to different blocks, but they also map to same line. Notice the block containing Q will map to this line 0 1 0 1 0, and the block containing R will map to this line 0 1 0 1 0. Did you notice that this Q comma R, they belong to different block, but they will also map to same line? Okay, and you can see P comma S, they will map to a different line. So finally, the point is, let me tell you, it is like this, that P comma Q, P comma S. So the point is like this, that P comma S, they belong to same block. Here you have P and here you have S. Okay, so they are in the same block, no problem. They will map to this, I can say this block containing PS. This will map to which line? This maps to which line? This will map to line 0 1 0 0 1. Okay, this line 0 1 0 0 1. This is binary. This is binary. So of course you can convert it into decimal if you want. It is not required, but if you want, you can convert it into decimal. So this is basically, I can say, line number 9. Okay, the block containing P comma S, that will map to line number 9. And what about the block containing Q comma R? Okay, there is a block that contains Q. There is Q here. So this is the block containing Q. So the block containing Q will map where? Will map to line 0 1 0 1 0. 0 1 0 1 0. Okay, so in the decimal, of course, you can find it. What is line number? Line number 10. The block containing Q will map to line number 10. Also remember, the block containing R, that will also map to line number 10. Okay, there is a block which contains R. That is your BR, I can say, block containing R. So this block containing R, this will also map to line, you can see 0 1 0 1 0. This block containing R will map to this line 0 1 0 1 0. In the decimal, this is also line 10 in decimal. Okay, so that's it. I hope you understood this point. The complete question, step by step, we are going. Of course, it is taking time because I am explaining. But if I don't explain, if I solve it directly, then it will not take this much time. Okay, is this clear? I am just making sure that you understand the question. What the question is asking, you understand each and every point. Okay, that is the reason every small thing I am telling you. So ultimately, remember the block containing P comma S, they will map where? They will map to line number 9 in the decimal. Yes or no? So this P comma S, they belong to same block. This is your block containing PS. They belong to same block, like this is P and this is S. they are words belonging to same block, and this they will map, this block will map to line 9. Okay, and also this block containing q, block containing r, they are different blocks. Okay, but they will map to line number 10. Okay, but they are different blocks. You can see these two, this and this, they are different blocks. I hope this point is clear. Now let's come back to question. The question was saying that this is the access sequence. The program is accessing these words PQRS, these four words. Program is accessing PQRS, PQRS like this, total 10 times. So total 40 accesses are there. Now just tell me from your observation, you tell me initially the cache memory is empty. We have a direct mapped cache memory. Initially the cache memory is empty. So tell me this P will be a miss. Yes or no? Definitely this P will be a miss. Okay. So when this P will be a miss, then what we will do? Just tell me. This is the cache memory. Okay, let me create the cache memory like this. This is the cache. This is the cache. And in this cache memory, somewhere there is line 9. Yes or no? And there is line 10. Agree? In this cache memory, there is line 9 and there is line 10. Agree? Yes or no? Very simple. Now you notice. First, you can see this P. Initially, the cache memory is empty. When the program will access this word P, then there will be miss because it is not available in the cache memory. So there will be a miss. When there is a miss, then what we will do? From the main memory, this block containing P, we will fetch to the cache memory. Yes or no? So we will fetch the block containing P comma S, because P comma S belong to the same block. Yes or no? So remember, when there is a miss, then from the main memory we will fetch this block. Okay, this block, fetch this block. I can say fetch block B, block containing P comma S. Okay, fetch this block from main memory. From main memory. From main memory, we will fetch this block which contains P comma S. Okay, because P comma S belong to same block. So this block we will fetch from main memory to cache. Okay, and of course it will map to line number 9, that we already know, that block containing P comma S will map to line number 9. So in this line number 9, I can put this block containing P comma S. Okay, that's it. Now just tell me, what about this Q? There will be again miss. Okay, when there is a miss, then what we will do? Why there is a miss? Because Q belongs to block containing Q, and that is different from block containing P comma S. Yes or no? We already know that block containing P comma S is different from block containing Q, is different from block containing R. Okay, they are different from each other. So you can see, when the program is accessing this word Q, then again there is a miss, because the block containing Q does not belong to the cache memory, is not present in the cache memory. So there is a miss. If there is a miss, then what we will do? For this miss, what we will do? We will fetch block containing Q. This we will fetch from main memory. Okay, from main memory. So now you tell me where we will put it. It will go to line number 10. We already know. So this will go to this block containing Q. This will go to line number 10. Very simple so far. Now you tell me, what about R? When we access R, again there will be a miss, because remember R belongs to a different block. Q comma R, they belong to different blocks. So remember, this is also miss, because block containing R is not in the cache. That is the reason there is a miss. If there is a miss, what we will do? We will again fetch the block containing R. This we will fetch. We will fetch block containing R from main memory. From main memory. So tell me where it will map to. In the direct mapped cache, every main memory block will map to unique line. So you can see here, this block containing R, will actually replace the block containing Q. Yes or no? So this block containing Q, it will be replaced by block containing R. Okay, very simple. Now tell me, what about S? Now when the program is accessing the word S, is there a hit or a miss? There is a hit, because the block containing S is in the cache memory. So this is a hit. Yes or no? This is a hit, very simple. What about P? What about P? When the program is accessing word P, is this a hit or miss? Yes, this is a hit, because the block containing P is already in the cache. So this is also a hit. Yes or no? That's it. I hope you understood the whole point. What is happening here? Okay. So you can easily see that for this S also there is a hit, and for this P also there is a hit. Okay. And remember one more thing, that no one will disturb P comma S. Do you agree with me? Because P comma S, they will map to line number 9. Like this is your line 9. See, here you will put block containing P comma S. Okay, but notice one thing, that block containing Q, block containing R, they will map to line number 10. So do you agree with me that no one is going to disturb the block containing P comma S? No one will disturb P comma S. Yes or no? P comma S will be hit, here also hit. Means only the first time this P is a miss. Only the first time this P is a miss. After that, no one is going to disturb P comma S. So P comma S will be a hit after the first miss on P. But remember, S is always hit. Did you notice? S is always hit. S is always hit. And what about P? Once miss, first time miss, then it is always hit. Yes or no? P is first time miss, first time miss, then always hit. Yes or no? This is a beautiful question. I hope you understood the complete analysis. What is happening here? Slowly, slowly, step by step, I'm telling you each and everything. I'm making sure that you understand the question. Every small part in this question you understand. That is the reason we are taking time. But once you understand this question, any type of any similar question, you will be able to solve very easily. Okay, is this point clear? Please tell me. So you can see P comma S, these are not blocks, these are words. Please understand. Again, I am telling you, some students, they just assume that P, Q, R, S, these are the blocks. So let me tell you that P, Q, R, S are not blocks. These are not block numbers. Okay. You can easily notice that P comma S actually, P comma S, they actually belong to same block. Okay, P is also here, S is also here, they belong to same block. So initially, because when we access P, then there will be miss, then there will be miss. Now this block we will fetch from the main memory to the cache memory, so automatically S is also coming. Now you can see, now when we access this S, now there will be a hit, because the block containing P comma S is already in the cache memory. Yes or no? And after that, if you access PS, 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 they will always be hit. What is the reason? The reason is Q comma R, they are not going to disturb P comma S. Q will map to line number 10, R will map to line number 10. Yes or no? So no one is going to disturb P comma S. So initially, the first access to P, that is a miss. After that, all the access to P, that is a hit. And every access to S, that is a hit. Very simple point. Okay, now you also tell me about Q comma R. So we have already seen the conclusion for S comma P. The conclusion for S comma P we have already seen. Now you tell me about the conclusion for P Q comma R. Okay, so P comma S we have already seen. Now you tell me. You notice that this was a miss. The reason is very simple, because this is your line number 10. Okay. Now notice that block containing Q, that will also map to line number 10. Block containing R, that will also map to line number 10. and these are different blocks. These are different blocks. B block containing Q, that is a different block than block containing R. Yes or no? These are different blocks. So notice that it's like this, that when we will access Q, then block containing Q will map to line number 10. And when we access R, then block containing R will map to line number 10. So they will replace each other, yes or no? Like every time what will happen, this R will replace Q, this Q will replace R, like that. Okay, yes or no? You can see initially this Q is a miss, and after that this is also a miss, but this R what it will do, it will replace Q. Okay, next time you can notice this Q, this will replace R. What this R will do, it will replace Q. Okay, yes or no? That's it. And so on. You can see this Q will replace R. This R will replace Q. Okay, and so on. So let me tell you about the final conclusions, some observations. The first observation you can notice that S is always hit. The second observation, P is first time miss. First time miss, then always hit. The third observation, what about Q comma R? You can notice R will always replace S. Can I say the same thing for S, that it will always replace R? R will always replace S. But remember, the first time S is, sorry, not. For R, what can I say? I will say R will always replace Q. But can I say the same thing for Q? No. The first time Q is not replacing R. R will always replace Q. Okay. But remember, this Q, first time it does not replace R. First time it does not replace R. First time does not replace R. But after that, after that, always replace R. Replace R. Okay, is this clear? And you tell me at the end who will be there in the cache memory? You are doing PQRS, PQRS, and so on. At the end, PQRS, PQRS, and so on, PQRS. At the end, you can see who will be there in the cache memory. At the end, of course, P will be there in the cache memory, S will be there in the cache memory, R will be there in the cache memory. Is this clear? So let me tell you here the fifth. At the end, at the end, because this was the access sequence PQRS, PQRS, and so on, PQRS. So at the end, you can see this block containing P, block containing S, that is basically same. And also this block containing R, this also will be in the cache memory. So at the end, you can see in the cache memory, this will be the situation that on the line 9, we will have block containing P comma S, and on the line 10, we will have block containing R. So I can say at the end, at the end, Q is not in cache. So these are some observations. That's it. This is the question. I hope you understood. So let's solve. Let's see. Let's see which option is correct. Every access to S is a hit. We have already seen yes, correct. Once P is brought to the cache, it is it is never evicted. Yes, correct. Okay. At the end of the execution, only R comma S reside in the cache. No. At the end, who will reside in the cache? Tell me. Option C. At the end, P also, R also, S also. These will be there in the cache. In the cache. But here it is saying only R comma S will be there in the cache. That is false. Every access to R will evict Q. That is correct. Every access to R will evict Q from the cache. So for this question, the answer will be ABD. This is a this is a beautiful question. I hope you understood this. The complete analysis of this question, did you understand? Please tell me. This is a very beautiful question. One thing notice, there is no new concept in this question. Nothing new. The same old concept, the same basic concept you need to apply. You need to apply direct mapped cache. First you do address division, then you notice that PQRS, these are not block numbers, so you find to which block they belong to. The address of PQRS is given to you. From these addresses you find to which block numbers, to which block addresses PQRS belong to. Then you will see P comma S, they belong to same block, same memory block. Q belong to some other block, and R belong to some other block. Then you see to which line they will map to, because it is a direct mapped cache. Every memory block will map to unique line. So you notice the line index in the address of PQRS, in the address of these four, you notice what is the line index. Then you will see that this Q comma R, they are in different block, but they map to same line. Okay, P comma S, they belong to same block, so they will always map to same line. Okay, so this is what you notice. Then you can easily solve this question the way we have done. Remember, in this question, you might be thinking this is a heavy question, this is a hard question, I cannot solve it, this is very hard. No, this is not a hard question, this is a beautiful question. The same basic concepts you need to apply. Okay, you need to read every line, you need to understand what this line is saying, you need to understand that PQRS, these are not block numbers, you need to understand that this is not a block number sequence. PQRS, these are words. So you need to find to which block they belong to. Whenever there is any question which has replacement, like in this question, there will be replacement. Whenever there is any question which has replacement, then always find the block numbers. Okay. So this is very nice, very good, beautiful question. I hope you loved it. And I hope you enjoyed the complete analysis of this question. You will definitely understand, you will definitely learn a lot of things from this question. And in the future gate exam, any similar type of question comes for direct mapped or for fully associative cache or for set associative cache, whatever type of question they ask, you will be able to, you will be easily able to solve it. Let's move on now. Actually, we made a typo in S. You can see this S is given to you 0x A262, but we have written 0x A264. So actually, it will be A262, 0x A262. But don't worry, it is a good thing that we made the typo only in the offset. Okay, you can see this is part of offset, right? The least significant 6 bits, that is offset. So we made the mistake only in the offset. We did not make the mistake in the block number to which this S belongs to. Also, we did not make the mistake in the line index to which it will map to. Okay, so we made the typing mistake when I was typing this, when I was copying this A262, then this mistake I made A264. But don't worry, this mistake only happened for offset. This is part of offset. In this question, if you notice, this exact offset does not matter. The only thing that matters is that number of offset bits is 6 bits. Yes or no? Okay, so this typo we made, you can easily notice, like for this S, what will be the offset? The exact offset does not matter. The point is very simple. That is the reason in this question, even though we made this typo, but it will not affect the analysis. The complete analysis that we have done, that is correct. The answer is correct, the complete analysis is correct, everything is correct, because the exact offset does not matter. If you remember, this offset does not matter. If you have, let's assume here B, then also it is fine. Okay, instead of this A, if you make B, instead of this A, if you make 0, instead of this 8, if you make D, then don't worry, the answer will not change, the analysis will not change. Because if you notice, the complete analysis depends only on block address, to which block they will map to which block they belong to. Okay, so one thing is block address matters for PQRS, to which block they will belong to. Also, it matters the line index, to which line they will map to. Only these two things matter. That is the reason this exact offset, what is this offset, that does not matter. The only thing matters is that number of offset bits, that is 6 bits, and that is fine. Okay, so just making this clarification. Okay, the complete analysis that we have done, that is a correct analysis. So let me write it here. Instead of this 4, actually this will be 2. So it will be like, instead of this 0 1, it will be like this. Okay, correct. That's it. So let me just make the corrections. Here you can see, instead of here it will be 2, so here it will be 0 0 1 0. Okay, just making these small corrections. You can see the complete analysis that we have done, that is absolutely correct. There is no problem anywhere. Okay, let's move on now. Let's solve GATE 2021 question. Consider a set associative cache of size 2 KB. 1 KB means 2 power 10 bytes with the cache block size of 64 bytes. Assume the cache is byte addressable and 32-bit address is used for accessing the cache. If the width of tag field is 22 bits, then the associativity of the cache. We need to find the associativity of the cache. Means, see, this is a set associative cache. Let's assume this is n way set associative. Means in every set there are n lines. This is what we need to find. We need to find in every set how many lines are there. Okay, so let's solve it. First of all, the associativity of the cache we need to find. So you can assume for a moment, assume it is n. Okay, let's assume it is, or you can assume like 2 power n. Okay, instead of n you can assume it is like 2 power n. Okay, or I can say e means 2 power n, because you know that the associativity, that will be a power of 2, like 2 power 0, that is one way set associative, that is direct mapped cache. 2 power 1, 2 power 2, 2 power 3, and so on. So the associativity, what you can do, you can assume that is 2 power n. Okay, now let's see. So we have set associative cache, the cache memory size is 2 KB. So first you find what are the number of lines. Number of lines, that will be the size of cache memory divided by the size of block. The block size is 64 bytes. So from here, this is 2 power 11 divided by 2 power 6, that is 2 power 5. These many lines are there. What about the block offset size, offset bits? Because the block size is 64 bytes, so for offset we need 6 bits. Very simple. Next you can see the width of tag, that is 22 bits, and the address size, that is 32-bit. So in the set associative cache, the address, the 32-bit address, we can divide into 3 fields. These 3 fields, these are basically tag, set index, and offset. For offset we need 6 bits. For tag we need 22 bits. This is given in the question. Okay, and you can see this total, this is also given, that is 32 bits. So tell me, for set index, this index means set index. So for set index, tell me how many bits we need. 32 minus 22 minus 6. So that will be 4. Yes or no? For set index, we need 4 bits. So what is the number of set? What is the number of set? The number of set is 2 power 4. These many set are there. In the cache memory, we have 2 power 4 sets. So the number of set we found, that is 2 power 4. Okay. Now you notice we are assuming the associativity is equal to 2 power n. So we have number of lines, that is 2 power 5. See, number of lines we have, that is 2 power 5. And we are assuming that in every set there are 2 power n lines. Okay, we are assuming we have already assumed that the number of ways basically, or I can say the associativity. Okay, that means number of lines per set. Number of lines per set, that is equal to 2 power n. This we have assumed. Okay, so you just tell me if number of lines is this and number of lines per set, that is 2 power n. So what will be number of set? Number of set will be equal to number of lines divided by, in every set there are 2 power n lines. Okay, you can see the number of set, that is 2 power 4. So 2 power n is equal to 2 power 5 divided by 2 power 4. So that will be 2 power 1. So from here n will be equal to 1. So this is one way set associative cache. It is a direct mapped cache basically. Okay, the answer will be 1. Very simple. Who रिकॉर्डिंग पॉज कर दी थी? कब हुई? ओ, ये कब हुआ? बस एक ही क्वेश्चन स्किप हुआ ना? सिर्फ ये एक? चलो ठीक है, वैसे भी इजी क्वेश्चन था, कोई दिक्कत नहीं है. ओके, आई विल डू इट अगेन इफ यू वांट इन द नेक्स्ट लेक्चर. Okay, so I think for this lecture, I think this is enough, right? Some questions you can solve like, okay, this question, this question. So there are some more questions. Okay, you can solve. So I think this is enough for this lecture. Don't worry. Only one or two questions. I think the recording did not. I will take them again. The questions which were not recorded, I will take them again. Don't worry. Okay, don't worry about it. So I think this is enough for this lecture. Okay. So this is enough for this lecture. In this lecture, we have done some gate PYQs of cache memory with complete analysis. We will continue in the next lecture. We are going to solve each and every gate PYQ based on cache memory in this series. So I can say this is gate PYQ of cache memory part 1. In the next lecture, we will continue and we will solve more questions, more gate PYQs of cache memory. So thank you everyone. Please like this session and please share your feedback in the comments. Did you understand each and every question? And also, did you love the complete analysis of each question? Okay, thank you everyone.